problem session 1, and in each problem session I will circulate a set of problems, 8 to 10 problems. We won't have time to work out all of them, so I will work out selected ones. The rest of them I would expect that each of you will work out, and most of the problems I have solved myself, so solutions are available, but I won't give you the solutions till I see you yourself working out the problems. And these are the Tuesdays and Fridays that I shall be available. You can come and check the solutions, you can come and discuss the solutions, and so on and so forth. Okay, we will start with 5.1 and 5.2 I have already done in the lecture class, so we start with 5.3. The problem is a network is given like this: E, the switch S is thrown out at t equal to 0. That is, it was closed earlier, it has been opened now, and then you have a resistance, an inductance L, another resistance R, and a capacitance C. This is the network. This current is I2 and this current is I1. Alright, the switch was initially on and it has reached a steady state, and the switch is opened at t equal to 0. It is thrown out. Determine the initial conditions for the currents I1t and I2t, that is I1 0 plus and I2 0 plus. You have to find out this and their derivatives, that means I1 prime 0 plus and I1 prime I2 prime 0 plus. These are the four quantities to be found out from the equation, from the network. Now obviously before the switch is thrown open, the conditions have reached steady state, and therefore I1 0 minus and I2 0 minus can be found out from physical inspection of the circuit. Okay. At t equal to 0 minus the inductor will act as a short circuit and the capacitor will act as an open circuit, and therefore if this is short circuit, then obviously I1 of 0 plus, I1 of 0 minus would be equal to E divided by R. Is that clear? From physical considerations. And I2 of 0 minus, because the capacitor is open, it has to be 0. Alright. Now regarding the primes, what you have to do is you have to find out the circuit at t greater than equal to 0 plus. Let us look at the circuit. T greater than equal to 0 plus, there is this voltage source E, and then the switch has been thrown open, alright, then a resistance R, an inductance L, this is I1, and then another resistance R and a capacitance C, and this is I2. Obviously t greater than equal to 0 plus, because the switch is opened, I1 of t would be identically equal to 0 because of open circuit. If I1 of t is identically equal to 0, what can be I1 prime of t? Obviously that is also 0 because it is a constant. Alright. So that is no problem. However, I2 0 plus would be found out from considerations of continuity of current in an inductor. You see, the current in this inductor L has to be continuous from 0 minus to 0 plus. Now therefore I2 0 plus would be equal to minus, you see I1 and I2 are in opposite directions, so minus I1 0 minus, and we know what this is, minus E by R. Is this point clear?
Excuse me, sir.
Yes.
Sir, as far as we will not be adding plus I2 0 minus, Where is 0? It's 0, but.
Pardon me?
Sir, you should also write I2 0 plus.
Yes, this is what we have written, I2 0.
I2 0 minus.
No, I2 0 minus, we have already said it is 0.
In case it's not 0, then we would have written.
Then we would have had something else, yes. You see, because it's a short circuit at t equal to 0 minus, so the current through the inductor at 0 plus, which is in this direction from bottom to up, is the negative of I1, and therefore it is minus I1 of 0 minus equal to minus E by R. The other part of the equation, other part of the problem, namely to find out I2 prime 0 plus, we shall have to write the differential equation. We shall have to write the differential equation for this mesh. Let us see what the differential equation is. It is Ri2 plus 1 over C integral I2 tau d tau plus V sub C 0 minus, okay, then plus L di2 dt, that should be equal to 0. Is that clear? At t greater than equal to 0 plus, this current is 0, and therefore I have only one mesh, Ri2 plus the drop in C, which is 1 by C integral I2 dt plus Vc 0 minus, plus the drop in L, which is simply L di2 dt. Okay. So, if I put in this equation t equal to 0 plus, Vc 0 minus is 0. Okay. And this would be from 0 minus to t. If I put t equal to 0 plus, then obviously this will also be equal to 0. Okay. This is also 0 for t equal to 0 plus. And therefore, all I have is di2 dt at t equal to 0 plus would be equal to minus R divided by L I2 of 0 plus, and I2 of 0 plus we have already found out to be equal to minus E by R, and therefore it would be simply E by L. Is that okay? Yes.
So why Vc 0 minus is 0?
Vc 0 minus is 0. Okay, that's a good question. Steady state, this is a short circuit, and therefore I2 is identically 0. C cannot be charged. Okay. See, for charging of C there is required a current, but since L is identically equal to 0, no voltage can be supported from this point to this point. To start with is a different story. That is, at t equal to minus infinity, the battery starts charging. Okay. But in the steady state, when steady state is reached, even if the capacitor had acquired a charge, it would have discharged, because it finds a very easy path here, short circuit. Okay. Where what we are considering is the steady state condition. All right. Okay, that takes care of 5.3. Next we consider 5.4. 5.4. The problem in 5.4 is the following. The network is this. Let me draw it. 10 volt. I will draw a simplified diagram. I don't want to draw many lines for battery. There is a switch which moves from A to B. That means it was like this, then it moves in this direction, t equal to 0. At t equal to 0, the switch S moves from A to B, and there is a voltage source 5 volt here. Then we have a 1 Henry inductor. The current through this is ILT. We have a 1 farad capacitor. The voltage here is V sub CT, and it is shunted by a resistance of 1 ohm. This is the circuit. The circuit has reached steady state in the position A, and then at t equal to 0 the switch is moved to position B. Determine the initial conditions for ILT and VCT, that is you have to find out IL 0 minus, VC 0 minus and their first derivatives, that is IL prime 0 plus, well obviously IL 0 minus would be the same as IL 0 plus. By initial conditions we mean conditions at t equal to 0 plus, because there are no impulses they would be the same. So, write down IL 0 plus and this is also equal to VC 0 plus. What you have to find out is IL prime 0 plus and VC prime 0 plus and also the final values, that is IL infinity and V sub C infinity. Okay. Let us look at the circuit carefully. First is when the circuit reaches steady state at position A, the inductor is a short circuit, the capacitor is an open circuit, and therefore IL 0 minus or IL 0 plus can be written down by inspection, and this would be 5 amperes, 5 volt. This is short, this is open, 5 volt across 1 ohm, and therefore the current must be 5 ampere. And since this is a short, V sub C 0 minus would also be equal to 5 volt. Is this clear? Okay. Now to find out the derivatives, we have to find out the conditions at t equal to 0 plus. At t equal to 0 plus, the circuit is this. The battery now comes as 10 volt, then you have the inductor 1 Henry, this current is ILT, then you have the capacitor 1 farad, this voltage is V sub C of t, and then you have the 1 ohm resistance. Okay. This is the condition at t greater than equal to 0 plus. All right. Now let us write to find out the derivatives of IL and VC at t equal to 0 plus. Let us write a couple of equations. All right. First you notice that for this loop, now in the matter of calculation of initial conditions, a bit of ingenuity. Now there is no blind mechanical rule. In fact, electrical engineering is quite different from mechanical engineering. There is nothing much of mechanical here. You have to apply your ingenuity and your intelligence. Now in writing this equation, you see we write 10, the driving source, equal to 1 Henry, then dIL dt. You see dIL dt has come in the equation. You have to seek those equations which give you the desired quantity, dIL dt plus, now this voltage I will simply write as V sub C, all right, simply as V sub C. I will not write in terms of the element equation, all right. Then I put t equal to 0 plus. Obviously dIL dt 0 plus would be equal to 10 minus Vc 0 plus. Now Vc 0 minus was 5 volt, therefore Vc 0 plus is also 5 volt, and therefore this would be 10 minus 5, and the quantity is 5, the unit would be amperes per
What about the
second.
current in the capacitor?
Oh, we do not care, because this potential we are writing KVL, that is the ingenuity. You see we are writing KVL, so this the driving source is equal to this drop across 1 Henry plus drop across 1 farad, fine, and the drop across 1 farad is VCT. We do not care what the current is, all right. Then that takes care of dIL dt. Now we have to find out dVc dt. Obviously if we want to find out dVc dt, we have to take care of the currents, because C dVc dt is the current, and therefore what we do is we write a node equation here, all right. If we write a node equation here, let me write in a different color. You see the current is minus ILT, the current going out, plus 1 farad dVc dt, okay, plus V sub C by 1 ohm, this current, the sum of these three currents shall be equal to 0. Agreed? And therefore, in this equation you have to write that equation. You see, we are not writing loop equations or mesh equations, both of them. No, we are writing one mesh equation and one node equation, because that is what gives us the desired quantity. And therefore, dVc dt at 0 plus would be equal to IL 0 plus minus Vc 0 plus, and Vc by 1 Vc by 1 ohm, that is why it is Vc. Of course, this also looks ridiculous, isn't it? A voltage is being subtracted from a current, but the suppressed factor is a 1 ohm, division by 1 ohm. So, actually we are differencing two currents, alright. So, and this, as you see, IL 0 plus is 5 numerically, Vc 0 plus is 5. So, this is 0 volts per second, alright. The quantities have been found out. Finally, what we have to find out is IL of infinity and V sub C of infinity. Obviously, IL of infinity would be, pardon me, this part. Okay, I'll repeat this. What I wrote was, I want to write a node equation here. The current going out through the inductor is minus IL, that is what I write here. Then the current that goes out through 1 farad capacitor is C, which is 1 dVc dt, C dVc dt, and the current that goes out through the 1 ohm resistance is simply Vc by 1. So, Vc, the sum of these three currents equal to 0, and then I say dVc dt at t equal to 0 plus is, I take this quantity and this quantity to the right hand side and substitute their values, alright. Okay. As far as infinite time value is concerned, when this circuit reaches steady state, once again the inductor becomes short, the capacitor becomes open, and therefore the current through this circuit would be 10 volt by 1 ohm. So, it would be 10 amperes. You see what has happened? Initial condition was 5 ampere IL plus, IL 0 plus. So, from 5 amperes it rises to 10 amperes, obviously exponentially determined by the time constant of the circuit, and Vc infinity after the infinity is again it is equal to 10 volts. It started from 5 volt, now it has risen to 10 volts, and that is the total solution of the problem. You see, a bit of thinking is needed. It is not routine, it is not mechanical that you write this and solve this and so on. In the solution also you have to find a simpler way. Was there a question? No. The next problem that is solved, we will skip now one problem at least. Next problem we will solve is 5.6 on the other side. The remaining ones are to be done by you. 5.6, the problem is this is an interesting problem. There is an excitation of IUT, that is a current source is switched on to a parallel combination of a G is a conductance and an L. The current through L is IL, and this voltage is V of t. This is the circuit given, and for the network shown it is given the initial conditions are that IL 0 minus is equal to 0, okay, and what you have to find out is Vt for 0 minus to infinity. This is part A, this is to be found out. Second, you have to show that Vt approaches delta t as G tends to 0. As the conductance tends to 0, which means the resistance becomes infinite, you have to show that the voltage appearing across Vt tends to delta t, an unit impulse, and then find the, not unit, some k, Part C is find K, the strength of the impulse. That is the question. Now we can solve it by differential equations, but it would be easier to solve it by Laplace transform. Why? Because there is no problem of initial conditions. Even if initial conditions are there, Laplace transforms can be used, but the situation will dictate to you what should be used, whether time domain or frequency domain. Okay. If you use the time domain, then you see V of S, let us take Laplace transform. V of S, that is the Laplace of Vt, shall be equal to the current multiplied by the impedance. The current has a transform I by S, alright, I ut, the Laplace transform is I by S, multiplied by impedance, which is simply reciprocal of admittance, and the admittance is because of a parallel combination G plus SL, alright, and therefore V of S is equal to I divided by S L S plus G by L. Is that okay? Alright, this is V of S, and therefore let me repeat it, V of S equal to I by L 1 over S plus G by L. Was this a step function? Yes, okay. Which I can write as have I made a mistake?
Yes, yes, sir.
So we can't write G and SL.
Pardon me? Yes. Why didn't you tell me earlier? 1 upon SL, okay. Therefore, it would be, let me simplify this. This would be I by S SL 1 plus S L G, okay, alright. Therefore, V of S is equal to this S and S cancels, S and S cancels, okay. So, I get I times L divided by, let me take LG common, then I get S plus 1 over LG, alright, S plus 1 over LG. This is equal to I divided by G, which is simply IR, okay. Capital G is the reciprocal of the resistance, divided by S plus R by L, and therefore I can take the Laplace inverse of this to get V of t as IR, then e to the minus R t by L. This is not complete, we must write multiplied by U of t. This is the voltage solution, and you can see that the voltage starts from IR and decays with time, alright. You also know, is there any question up to this point? No, do not allow me to make a mistake. You also know that the time constant of the circuit is the time required for the voltage to drop to 1 by Eth of its value at t equal to 0, and therefore the time constant of the circuit is simply L by R. So, this is L by R, and this value is IR divided by E, alright. This is the time constant. Now, part B says show that the voltage response approaches an impulse as capital G tends to infinity, that is, I am sorry, 0, that is capital R tends to infinity. Now, you see that if capital R increases, the height at t equal to 0 increases, and capital T, which is L by R, decreases, and therefore with variation of g, the situation would be like this. If I plot Vt versus t, this may be for one time constant. If the time constant is increased or decreased, capital G decreases means time constant decreases, then the curve would be like this. Alright. If we further increase capital R, that is, if we further decrease capital G, maybe the curve is like this. And obviously, as capital G tends to 0, V of t tends to an impulse function k delta t. This is from physical reasoning. To establish it on a sound basis, on analytical reasoning, what we do is we take part C. If we integrate Vt from 0 to infinity, alright, if we integrate this, then you use the expression and integrate, you can show that this expression is simply I times L. I have carried out the integration here. This expression is simply I times L. Now, what does it show? It shows that as capital G varies, the area under the curve remains the same, and that is the property of a delta function. A delta function, the area under the curve remains the same, but the duration keeps on decreasing and decreasing. Duration we define here by the time constant, capital T. As capital T goes to 0, obviously the curve tends to an impulse function whose strength, instead of unity, it is I times L. So that answers part C and also strengthens the physical argument given in part B. That is what you have shown.
No, sir, from the
yes,
expression,
and that area under the curve is constant. Don't we need to show that at when G tends to 0, this whole of the area is present at
t equal to 0, because the time constant is 0, capital T is 0. So in 0 time it falls to 1 by E of its value. In 0 time it falls to 0 at 0 of its value also. There is nothing sacred about 1 by E. It could be 1 by 100, it could be 1 by 200, or it could be 1 by infinity, even then. But I agree, it is still a physical argument. Okay, the physical argument.
Can we establish this fact from the formula of Vt, from the expression that we have obtained for Vt?
Can we establish this fact from the expression? Yes, this is what I am going to tell you now. Yes, this is precisely what no, first let me take the physical situation. In the physical situation, as capital G tends to 0, alright, it becomes an open circuit. So what you are doing is you are applying a unit, a step, open circuit. Capital G equal to 0 is R equal to infinity. So it becomes an open circuit. Now IL of 0 minus is 0, and therefore initially when you apply the unit step, it is an open circuit. On the other hand, unit step stabilizes immediately. Okay. So what happens is this current capital I is being forced into L despite the fact that it tries to resist, and this is a singularity condition, that is the step current from 0 it is being forced to become capital I. The derivative therefore is a delta function, derivative is infinitely large. Derivative of an unit step is a unit impulse function, and therefore the current, the voltage which is L di dt, this is small I establishes from 0 to capital I instantaneously, and therefore the voltage must be a unit impulse function. And this argument can now be extended to the equation, and I leave that to you. This physical argument can be translated in terms of a mathematical argument in terms of the equation. The next problem that we solve, unless there is a question here, the next problem would be 5.8. 5.8. I have skipped 5.7. Okay, 5.8. That is a very interesting problem. There is a voltage source V, a resistance R, and a switch S, which goes from the point A to the point B at time t equal to 0, and to B is connected a capacitor C, then to S is connected an inductor L. This current is I of t. This is the circuit, and the conditions of the problem are: before the switch moves from A to B, steady state condition prevailed, and therefore I of 0 minus is simply equal to V by R. Agreed. Then you have to find out the current IT, obviously for t greater than equal to 0 plus. All right. I of 0 minus was V by R. How does the current behave when the switch is moved from A to B? Now let us argue physically first. Physically, you see, a current V by R is established in L, and when the switch moves from A to B, all we have is an initial magnetic energy in the inductor. The capacitor is initially uncharged. There is no electrostatic energy. There is no energy stored in the electric field. Now this current in the inductor, the flux in the inductor will try to decay, because it finds a short circuit. At t equal to 0 plus, capacitor is a short circuit. So this current tries to flow through this, and in the process charges the capacitor. Any current flowing through a capacitor charges the capacitor. So this current will start charging till the voltage across the capacitor as a result of its charging is the same as the voltage across the inductor. You see, voltage across the inductor is L di dt till the two voltages equalize. If the voltages equalize, then there should be no current. All right, and therefore what happens after that? The capacitor now, it is a steady state. The capacitor immediately starts discharging through L, and this process continues. It is a seesaw situation. In other words, you will get pure oscillations. Now, as I told you, this part of the circuit is a passive circuit. How come it is able to generate oscillations? How can it behave like an active? Well, in practice it cannot, because an ideal inductor is a dream element, so is an ideal capacitor. There would be resistances, and therefore what you will see in practice is a decaying sinusoid, but in theory it can be a pure oscillation. Now let us look at it mathematically. Mathematically the current, let me write it here because the circuit is here. The current I of t at t equal to 0 plus, the situation is that the switch has come here. So this part has become invalid at t equal to 0 plus, and I of t, if this voltage is V, then I of t is equal to minus C dV dt. Do you understand the meaning of the negative sign? Why it is so? Because V is considered positive here and negative here. So the current through the capacitor is in this direction, C dV dt is in this direction, whereas the current IT has been taken in the opposite direction. Is that clear? You have to be very careful about this sign. So I of t is minus C dV dt. Now this is minus C d dt of what is V in terms of L? It is L di dt, and therefore this is L di dt, and that does it. That gives you the equation I of t equals to minus LC d2I dt2, and it is I that we have to find out. Therefore what we have is LC d2I dt2 plus IT is equal to 0. Alright. Now you can solve this differential equation subject to the condition that I of 0 plus is equal to V by R. Okay. This is a differential, this is second order differential equation, and therefore 0 minus is the same as 0 plus. One initial condition does not suffice. You also require I prime of 0 plus, isn't it? This is second order differential equation. Now let us look at this. What is I prime of 0 plus? Physical considerations or mathematical considerations? Can someone tell me what would be I prime of 0 plus? Pardon me?
It will be an exponential.
Exponential. No.
At 0.
Why is it 0? 0 is the correct answer. But why? Because? No, that is not the reason. How do you know? At 0 plus the current could be rising or falling.
So the decreasing inductor is the same as the rise in the capacitor.
So
that ain't
current
no
cannot
argument.
change through the inductor.
Pardon me?
So current cannot change through the inductor.
So current cannot change. That's why I 0 minus is equal to I 0 plus. Yes.
So we can have one thing that the voltage across the capacitor.
That is correct. That is the clue. You see, voltage across the capacitor Vt is simply equal to L di dt, and Vt at t equal to 0 plus is 0, and therefore di dt 0 plus must be 0. Do you see the argument? You must be able to justify. Okay. The justification is at t equal to 0 plus, this is the equation which is valid, and Vc of 0 plus is equal to 0, and therefore dI L dt at 0 plus must be equal to 0. So we have two initial conditions. Now you can solve this. Alright. Instead of doing it in the time domain, even though initial conditions are there, it is instructive to do it in the frequency domain. So let us take the Laplace of this equation. Let us take the Laplace of this equation. Obviously what we get is LC, the Laplace of second derivative is S squared I minus S I of 0 plus minus I prime 0 plus. Do you remember this? Okay. Then plus I would be equal to 0, and therefore what we get is I S squared LC plus 1, which takes care of this term and this term. This is 0, would be equal to LCS, and I of 0 plus is V by R. So that's it. That's what it is. Okay. Which means that capital I would be equal to VLC divided by R, S divided by S squared LC plus 1, and I can write this as VLC by R, S divided by S squared plus 1 over LC, and then you have to multiply by LC. This cancels with this, so it is equal to V by R, S divided by S squared plus 1 over LC, and any table of Laplace transforms will show you that under this condition I of t is equal to V by R cosine of square root of this. So t divided by square root LC multiplied by ut, and so there is a co-sinusoidal oscillation in this circuit. Okay, it is instructive to do this because we get a chance to review our knowledge of Laplace transform. Okay, and the second derivative of a Laplace transform, it also shows the how I prime 0 plus has to be determined. So this problem is very instructive. Any question on this? Finally, we work out 5.9. 5.9 is also a peculiar problem. 5.9 says that you have a resistance R, a battery V plus minus, an inductor L1 and then an inductor L2. Across L2 there is a switch, and the switch was initially closed and thrown open at t equal to 0. For the circuit shown, the switch S is opened at t equal to 0 after the circuit had been in steady state, okay, which means that if this current is I of t, then I of 0 minus would be simply equal to V by R. Okay. What you are required to do is to find out I of t for 0 minus less than t less than infinity. You have to find out the current IT. Something peculiar happens. Let us look at it from physical point of view. For an electrical engineer, physical concept has no replacement. You can solve differential equations, you can consult Laplace tables, you can find the spectrum by Fourier transform and so on. You can do hundreds of different things. You can write algorithms on the computer, you can simulate equations, you can find however complicated, but there is no replacement for physical concept. Let us look at the physical concept. You see at t equal to 0 minus, this inductor was shorted. This inductor was shorted, and therefore L1 carried all the current and the magnetic flux was generated by L1 only. Through L2 the current was 0. At t equal to 0 the switch is open, and therefore whatever current was flowing through L1 is now being forced to pass through L2, because otherwise the current cannot flow, and the current requires a path, and therefore this is a case of singularity. This is a case in which the current in L2 has to change instantaneously in order to establish a flux, and provide a path, provide a closed path for the current. Alright, this is a case of singularity, and one has to be extremely careful in solving this problem.
So why not a current change in L1 instead?
Current has to change in L1 also.
But instantaneous change.
Yes,
L1 as well as L2.
you will see how it changes. Okay, the physical situation should be clear now. Now the question is to find IT for 0 minus less than equal to t less than equal to infinity. Okay. One of the things that I confused you intentionally with is the question of current through L2 at t equal to 0 minus. Is it really 0? It is 0? Well, at t equal to 0 minus, L2 is a short circuit, S is also a short circuit. So there are two short circuits in parallel. At t equal to 0 minus, it is a short circuit because the current has established the steady state. There is no change of current.
So, but at times equal to minus infinity,
Yes.
when the switch S was thrown, it was closed, then there would have been no current in L2. Now, so since it has been shorted, there will never be any current in it.
All that has been infinite time ago.
But since then, sir, the current
Since
has been
then-
flowing through the short switch only, not through L2, sir.
But L2 also provides a short. At t equal to
Short only if initially some current goes, but when the switch
initially some current goes. No, this is a degenerate situation again, because it is being shorted, because a switch is being thrown open. It is a degenerate situation,
Sir, owing to the fact that when the current
and we do not
starts-
know at t equal to minus infinity what happened, we do not know. We are concerned at t equal to 0 minus when S is closed and V has been there for a very long time.
So we can have two situations.
but since
So
there is a
L2
short
can,
across the
L2 cannot
inductor,
be a short unless a current flows through it. And since S is already a short, so no current will start flowing in
Flow
L2.
through
Therefore,
L2
the
at all.
situation of it being short circuit at 0 minus doesn't exist.
This current after coming here, when this is short, this is also a short, L2 is also a short,
Initially, it's an open circuit at T minus
so
infinity.
but the very
doesn't matter.
So,
The current
but we
has
cannot
established.
So how it will
But
act?
whatever current will be there, that will be discharged.
Who will oppose it? Once the current has established, this has become steady. You agreed that the current, steady state current is V by R.
Yes, sir.
Okay, the current is steady, there is no DIdt. There is no DIdt. So the voltage across this shall be 0. If the voltage is 0, obviously it is a short circuit.
So it depends when the switch was closed, sir.
Switch is closed after t equal to infinity. From minus infinity to 0 minus the duration is infinity.
So but then how do you compare
Suppose
how
we
much
consider
current
a case
flows
that
between the two shorts?
at t equal to 0,
Yeah.
this is initially L1 and L2 are relaxed, and we have
Initially L1 and L2 are
so
not
suppose we
relaxed.
consider a case,
Ah.
and we have thrown the switch such that now this has short, L2 is shorted.
Hmm.
Okay. Now whenever even a slight bit of current will tend to flow through L2, it will be acting as an open circuit because it will oppose the current, and that current will be tending to flow through the short. This situation will prevail up till infinity. And at infinity, this is now the same thing, that the current at infinity would be the same as here at 0. Fine.
That's not the that's not the
So
case.
there is no magnetic energy in L2.
Where?
In L2. So
Oh, there will be a magnetic energy.
So there is no current passing through it. Then
That is what I am not agreeing
By
with
this we
you.
are assuming that the battery was installed before the switch was closed.
Battery was installed before the switch was
Yes,
closed.
then only
Yes.
current would start.
Okay. Look, you see, the history is not known. How battery was, but you are looking at a situation after infinite amount of time. You see, after let us say 47 years of independence, you are not concerned with who fought whom and all, you are only concerned with your independence. Alright? Who are the people? Most of the young generation doesn't know who are the people for whom you are now with your head high and all that. So, we don't know the history. What we know is that at t equal to 0 minus, the current driven from the battery, drawn from the battery is V by R. The current after reaching here finds two short circuits. One is through the switches, L2 is no better than a short circuit, because for a steady current L2 cannot develop a voltage across it, therefore it is a short circuit. And if it is a short circuit, identical short circuit, there can be differences between short circuits also, there can be incremental resistances, but these are ideal cases, and therefore the current through L2 is half of V by R. And I2 0 minus, no,
So one thing,
not I2, just a minute, IL2 0 minus is equal to V by 2R. Yes.
that means we can consider the current through L2 depending upon our convenience.
No, it is not a convenience. You make a circuit and allow it. The best test is experimental test. Allow it to stand. Why not?
This is the ideal situation.
No, we have a resistance here, nothing will burn. You take a battery, connect a resistance and connect two inductors, short one of them, and allow the circuit to stabilize. Measure the current through the inductor and through the short circuit, it will be exactly half.
So, but the inductor and the short circuits are not resistanceless.
There will be slight difference, but that can be attributed to the resistances.
So if we have the resistance, then we can say that half current will flow. That's fine.
This resistance.
No, sir. These have some resistances.
No, this is a, as I said, it's a degenerate case. It's an ideal case.
Yeah.
You take R1 and R2 and allow R1 and R2 both to go to 0, you will see that current will be exactly half. Current division. No, current division. R1 by R1 plus R2 and R2 by R1 plus R2. Okay, as in the limit it will be exactly half. This is a degenerate situation and one has to consider that. And that is how flux shall be instantaneously established in L2, not otherwise. Okay, so the condition, I have a few minutes now, I will allow you to solve the problem yourself, but the condition for finding I of 0 plus would be the principle which you have not utilized so far. What is that principle? Continuity of flux. alright. Flux cannot be increased or decreased instantaneously, and therefore what we have is at 0 plus I 0 plus L1 plus L2 would be equal to L1 I L1 0 plus L2 I L2 0 plus. This would be the condition for finding IL 0 plus and I am sorry I of 0 plus, I of 0 plus, and your equation at t greater than equal to 0 plus, well this gives the initial condition of I 0 plus.
So
yeah.
should we not have 0 minus on the right hand side?
Yes.
0 minus on the
Right hand side of this equation.
oh yeah, I am sorry, I beg your pardon, yes, thank you. Here I L1 0 plus and I L1 0 minus are not the same, isn't that right?
Yes.
I L1 0 plus, how is it related to I 0 plus? Identical. Similarly I L2 0 plus would be identical to I of 0 plus. Had I written I L1 0 plus and I L2 0 plus here, it would have been a Himalayan mistake. I can afford to do that, you can't, alright. Okay. So from here you find I 0 plus, then at t greater than equal to 0 plus, obviously the equation is I V equal to Ri plus L1 plus L2. Now you can combine the two, because di dt does not involve the initial conditions, that is why you can combine the two, L1 plus L2 di dt, and you solve this equation. You solve this equation. Obviously the solution to this equation without doing anything else, you can take Laplace transform and do it, or you can do a first order differential equation solution, but in any case the solution would be of the form I equal to some constant k, k1 plus another constant k2 e to the power minus time constant would be r divided by L1 plus L2 times u of t, alright, from which, well, k1 can be found out immediately by allowing t to go to infinity. If t goes to infinity, what is the current again in this circuit, IT, again V by R. Okay, so we know k1 would be equal to V by R. For k2 now you have to put t equal to 0 and find out k2 and then the total solution. Well, I will leave the rest to you. Okay, fine, thank you.